Okay, so we're exploring Chapter 5 here, Science 9. We're talking about the atomic model. So you will see in science classes as you move through high school, you'll learn about the atomic model a little bit more. This is your first kind of look at the atomic model. Now, what are we talking about atomic models? Well, we've talked a little bit about the concept of an atom and how scientists over the years have viewed that or visualized that has changed. And so as science grows and we learn more and more, the models that we use to describe what we're seeing changes over time. So let's talk about the atomic model. First of all, what is an atom? And if you have the notes in front of you there, you should have some blanks. I'll highlight the blanks that you should fill in your notes. But an atom is considered by scientists to be the smallest part of matter. And we talked a little bit about this, I think, right? When you get down to an atom, if you were to divide something, cut something in half 1 billion times, you might be able to still cut it in half, but there would be a point where you'd get down to the smallest particle, the smallest little piece of that substance. And scientists have theorized that to be called the atom. All elements and compounds are composed of atoms. And one atom is the smallest unit of any element. So we have learned that inside an atom there are tiny little things that make up the atom. But if we're talking about a sample of, let's say, carbon, the smallest piece that is still carbon, fully carbon, the smallest piece would be called an atom. That would be the smallest little chunk of that carbon that's still carbon. Anything smaller than that would be things like protons or neutrons or electrons, the things that make up an atom. Okay? So the smallest piece of an element that still retains all of the properties of the element would be called an atom. All right, atomic models. Different models of the atom have evolved over time. Early theories of the structure of matter were not based upon experiments. So early theories of the structure, that's your blank there, were not based on, and you're thinking, what kind of scientific model is not based on experiments? Well, back in the day, we're talking about thousands of years ago when the Greeks started thinking about this concept. And the Greeks didn't perform scientific experiments like we did today. Instead, they just thought logically about things. They believed strongly in the purity of thought and reason. And they thought that that's all they really needed to understand the world around them. So they kind of did thought experiments. They logically kind of thought through things, and they kind of came up with this concept of the atom. A philosopher called Democritus first sort of coined the word atomos, which is Greek for atom. That's kind of where we get that word atom from. But they didn't do any experiments, so they were limited a little bit in finding out some of the greater details. As scientists began to study the relationship between several physical phenomena, now phenomena are just like things that happen, okay, like observations, okay, such as electricity. That was a big one. They're like, oh boy, we got to figure out electricity, how this works. And the other one was magnetism. So when you talk about magnets, when they saw magnetism and electricity in action, they were like, wow, we need to study this further because something's going on that we don't really fully understand. They began to develop different models about atomic structure. So of course, structure, that word means how it's put together, right? How literally it's built. And so if we know how an atom is built, we might be able to better understand things like electricity and magnetism. So they decided we need to do some more research here. We need to do some more study. We need to figure this out. Okay, so here's Democritus. We are going to talk a little bit about Democritus, the guy I mentioned here. About 400 BC, the Greek philosopher Democritus, and I guess you got Democritus for a fill in the blank there. The Greek philosopher Democritus, who began the search for a description of matter, asked, could matter be divided into smaller and smaller pieces forever? Or was there a limit to the number of times a piece of matter could be divided? Was there a limit to your blank is number.
They questioned a lot of things.
Oh, well, yeah. No kidding. I mean, when all you do is sit around in your toga and think about the world, I guess you come up with a lot of questions, right? You just sit on the steps of the Parthenon there, and you think about things, and you talk, and you fix your toga, and you talk, and you have the leaves around your head there, and you talk. I don't know. I'm being silly. You have to eat grapes like this, yes, and people fan you with these big fans, and I don't know what else do Greeks do. I guess invent the Olympics and stuff. Yeah. So in between your shot put or things like that, you got to talk about science. Anyways, yeah. So they did. They talked about a lot of things. That's right. Okay. So his theory, Democritus, he figured that matter could not be divided into smaller pieces forever. He decided that this was not logical. You could not divide something into smaller pieces forever and ever and ever, which was exactly true. There must be, eventually, the smallest possible piece that would be obtained. So you could divide something for a long time, but you would eventually get down to the smallest complete piece of that substance, whatever that was. That's what he figured in his mind. So the piece that would be the smallest piece would be indivisible. So they would figure that there would be a limit to how much you could cut things, and that piece would be completely indivisible. Now, indivisible means not being able to be divided anymore. He named the smallest piece of matter atomos, meaning not to be cut, or could not be cut any further. So something that was indivisible, the meaning of that would be atomos. And that's where we get our modern word atom from, right? Okay, so that's the Greeks. They didn't do scientific experiments, but they thought logically and philosophically about things, and this is what they come up with, which is actually pretty incredible. Because the big picture there is really there, right? We're talking about an atom, the smallest piece that would retain all of the characteristics of the matter.
How would you find that out without, like, either doing experiments or...
Again, just thinking through logically, right? They just thought philosophically. But along came John Dalton in the 1800s, okay? So you got some more blanks here to fill out now. John Dalton. So Dalton is his name. In the 1800s, and he was a school teacher. Yay, school teachers. Woo! He came up with a few important things. He said that all matter is made up of atoms. That kind of a thought that was already there, but he added to that. Atoms are indivisible and indestructible. Kind of already what Democritus said. He confirmed that, you know what, I think that is absolutely true. He also said some more things. Yeah, where's the blanks there? The atoms are indivisible and indestructible, meaning that they can't be destroyed. You cannot destroy them. That's the smallest particle piece, and it's indestructible. It cannot be exploded, cut, blown up, split apart in any manner. This is what he said.
Really?
This was John Dalton's theory. This was John Dalton's theory back in the 1800s. Okay, so some of this we still think today, some of this we don't. So we're exploring now what John Dalton thought about the atom, and he's adding to what Democritus thought. So all atoms of a given element are identical in mass and properties. So a second point that he discovered, or he determined, was that all atoms of a given element are identical in mass and properties. So if you have an atom of nitrogen, and over here on the other side of the room, there's an atom of nitrogen. Same atom from the same element, same kind of atom, they're going to have all the same properties, and they're going to be identical in mass. Okay? So atoms of a given element are identical in mass and properties. Compounds are formed by a combination of two or more different kinds of atoms. Okay. So all the compounds that we see, all the different materials that we know of or can make, come from a combination of atoms. Okay? Formed by so combination is your word, of two or more different kinds of atoms. So water, H and O, H2O. Hydrogen and oxygen. Carbon dioxide, carbon and oxygen. Ammonia, nitrogen and hydrogen. Magnesium sulfate, magnesium, sulfur, oxygen. So the atoms that we kind of know about on the periodic table over there, if you take little combinations of them, they make compounds. And there's a whole bunch of different combinations that's is possible there. Okay, he also said that atoms can neither be created nor destroyed. So these atoms are in existence, and the compounds that we make have to come from already existing atoms. If some kind of reaction happens and you have a new substance, he's basically saying that new substance did not just appear out of nothing. It had to come from something. So when you find a fried egg on the floor, you know that didn't just appear out of thin air. It didn't just like appear from nowhere. Magic. It came from somewhere, right? And so anything we see had to come from something that was already existing before. So it's just a collection of different types of atoms put together in a certain way under some certain conditions. But atoms cannot be created out of nothing, nor destroyed to oblivion and disappear. So everything's kind of got to be reshuffled. Guys? So, J.J. Thompson. J.J. Thompson. Now, there's no P here. It's not Thompson like some of you. I think there's some Thompsons in the class here. Right? You guys have a P in your name, right? Thompson? Right. This is Thompson without a P. It's not as common. But again, in the 1800s. So what did J.J. Thompson do? Okay, paying attention here, class guys? To your notes, thank you. And to me. Until the end of the 19th century, the concept of the atom was similar to a small, solid billiard ball. So a billiard ball is like a pool, like when you're playing pool, you know? That's what a billiard ball is. So a small, solid billiard ball. And Thompson is the other big blank. So John Dalton, we didn't discuss this, but he figured that atoms were solid, indestructible, so there's nothing different inside of an atom. He figured it was like a solid steel ball or a solid billiard ball. And at this point, J.J. Thompson thought that as well. But in the year 1897, should be on the back page of your notes there now, in the year 1897, Joseph John Thomson, J.J. Thomson, totally changed the view of the atom by discovering the electron. Thomson's atomic theory, so here's where the atomic theory changed now. He said, listen, the atom has to look a little bit different than what we thought. There's something we found out. Thomson's atomic theory suggested that the atom is not indivisible, but that it was made of smaller pieces. Electrons and protons. Now, to be fair, he didn't really discover protons either, but now we know that the smaller particles of an atom are electrons and protons. So those are inside of each atom.
So he didn't really discover them, he just kind of just like...
Well, he did. He discovered that there were other particles that were different than the actual atoms that he was studying. There are other particles that were common to other atoms that were different than those atoms, and those were electrons. So he basically discovered the electron. He didn't discover the proton. We'll see who discovered the proton here next. But so J.J. Thomson's model kind of looked like this. So notice, this is sort of the model that was prevalent at the time. It was like a solid model. But now he said, hey, the model actually has different pieces inside of it.
It keeps getting complex.
Yeah, it gets more complex, right? So I think probably these red things would be the electrons that he thought were kind of inside this ball. So an atom, he thought, consists of a sphere. So he thought it was pretty circular, like a ball. A sphere of positive charge. Sphere of, where is that? Positive charge. With negatively charged electrons, should be electrons, embedded in it. So it was like you've got this ball and you've got this sort of mush, okay, that's all positively charged, and inside you've stuck these negative electrons in there. So it was kind of like a ball of cake or a ball of pudding, and inside the pudding were like little pieces of fruit, and those little pieces of fruit were like the electrons. And as a matter of fact, he called his model of the atom the plum pudding model. The plum pudding model, which is kind of funny, but he was English and they ate a lot of plum pudding and everybody understood what that meant. So it's plum pudding. Now, where are the blanks in this one here? The positive and negative charges in an atom are equal in magnitude. So they're opposite charge, but they're equal, so they completely balance each other off. One negative and one positive completely balances each other off, due to which an atom is electrically neutral. So because the positives and the negatives are equal but opposite in charge, the atoms themselves are neutral. That means it has no overall positive or negative charge. All right, the next guy to come along here was Ernest Rutherford, and he was in the 1900s, and he actually studied in Canada, here where we live. He studied in Canada for a little while, out in Ontario, I believe. But he had a major contribution to the model of the atom that we understand today. So Rutherford shot positively charged particles, okay? So now we won't talk about how that happened, but here's a little picture, okay, of this little radioactive material inside this little box. And there was a little hole in it, and so that the radiation or the positive alpha particles would actually come out that hole in a predictable direction. And outside of that hole, he placed this thin sheet of gold foil. So that's what it looked like. Rutherford shot positively charged particles at a very thin foil of gold. Now, I need to pause here because some students initially have a lot of problem with this. What do you mean he shot particles through gold? Isn't gold like a metal? How do you like shoot things through a metal? Well, gold has the property of being very... What's the technical term there? That you can spread it out, you can pound it into a thin sheet. Malleable. Yeah, malleable. It's very malleable. So you can actually squish or pound gold into a very, very thin, micro thin sheet. And actually, I don't know if you've seen the NASA space, the astronauts, their visors that they look through. If you've seen the pictures, it kind of looks like it has a gold sort of like reflection off of it. Well, those visors, I believe they're still the same today. They have a thin sheet of, they used to have a thin sheet of gold actually in those visors, and you could see through it, and it protected the astronauts from radiation from the sun.
So if you touch it, it won't just shatter?
No, it won't just shatter. No, it's a thin film of gold. And not very many atoms thick almost. Like it's so thin, right? Not so thin. And so you can actually see through gold. It's so thin. So it wasn't that thin, but it was a very thin, sort of like, I don't know have you ever eaten a caramel bar? You know the caramel bar with the caramel in the middle of it? Well, in those packages, you know how they kind of have a gold kind of like foil inside those packages? I always thought that was cool as a kid. But anyways, if you think about that, that's something similar to what would happen here in this experiment.
And it's super cheap.
Now what happened here was that most of the particles passed right through this gold sheet. And honestly, what Rutherford had expected to happen was these large, fast-moving alpha particles would literally like blow through this thin gold sheet. He likened it, and he said, what I expected was basically these alpha particles were like cannonballs shot out of a cannon through a thin sheet of like toilet paper. So think about toilet paper and a cannonball, or even like a bullet from a big high-powered rifle. You would think that bullet is probably going to go through the toilet paper, correct? Well, that's exactly what he thought, but he saw something very different. Most of the positively charged particles went right through, but a few actually bounced back as if they were deflected by something very massive and positively charged. So your blanks look like this, but a few bounced back as if they were deflected by something very massive and positively charged. So just hang on. So just consider this. If I actually had a rifle and I was shooting a bullet through a piece of toilet paper over there, and that bullet actually ricocheted off the toilet paper and bounced back and hit the wall beside me, do you think I would be surprised?
Yeah.
Be like, what did that just hit? Whoa, what's going on? That's exactly what Rutherford thought. He's like, this is incredible. And how he detected that was here's the box, here's the alpha particles, Here's the thin sheet of foil. And around here, he had a detector plate surrounding this foil. And he saw that most of the particles passed right through and landed right here and hit this detector plate right here. But some deflected off, and some even bounced back like to here towards the direction of the box there. And so that's when he thought, well, this is really, really strange. Some particles deflected. And so he theorized that inside of an atom itself, there must be some really strong, formidable force inside the atom that is causing these particles to be deflected. And so Ernest Rutherford, he determined this. He determined that all of the atom's positive charge and most of the atom's mass is concentrated at a tiny point in the center of the atom called the nucleus. So he theorized, or he determined, he guessed that there's got to be something called a nucleus, or something like a nucleus in the center. And the particles that were kind of shot through, most of them went around the nucleus. But some of them, when they got close, actually bounced back or were so close that they got deflected away. And so this is what he thought was happening, and he theorized this nucleus in the center of the atom. Okay, so electrons surround the nucleus. So Rutherford figured that, hey, okay, Thompson, okay, yeah, you're legit. I guess what you figured out is true. Let's try and merge what we've found here together. And so he said, well, if there's a small positive dense region in the middle, those electrons must be on the outside somewhere floating around. And that's what they figured. Electrons surround the nucleus and occupy most of the atom's volume. So even in this picture, this is not a fair representation of this picture. The nucleus here is super huge compared to really what it really is. It's much smaller. It's like just a little pinpoint, really, in this diagram. It's super duper small. And the electrons are flying around so fast that they fill up this whole region. So it would be like a small eraser, okay, like the eraser in the end of this pencil. This would be like the nucleus in this whole room, if this whole room was an atom. This would be the nucleus. And then the electrons go so fast that they would fly around and like you know when you turn a fan on and you have like these blades and they turn and they go so fast that you see this circle. You don't really even see the individual blades anymore. You see this circle. That's kind of like electrons. They fly around so fast that they occupy the whole space of the atom, but you can't really see where they are. You just kind of see the region where they would fill up. So the nucleus is super small, but super massive. It's very, very dense, and so it's very heavy, and the electrons are very, very light. Like it's almost like they have no mass at all. But they're so fast, they fly around so much that they fill up the rest of the volume of the atom. All right, so moving on. Who's next? Who contributed now to this model of the atom? Remember, we had basically no model. The Greeks just were thinking about this. Okay, it's got to be something. We don't know what it looks like. Whatever, you guys can figure that out. And then Dalton comes along and says, hey, you Greeks said a lot of good stuff here. I think it's like a small solid lead or a steel ball, like a billiard ball. And then Thompson came along and he said, hey, inside that solid ball there's got to be certain negative charged particles in there. Rutherford came along and said, hey, that positive mush, Thompson, that you said, I don't think it's a positive mush. I think there's an actually small dense part where the positive exists. And so now we've got Niels Bohr coming close to the end of our exploration of the models. Niels Bohr was a Danish physicist, and based on his research of Rutherford's findings, he determined that electrons are arranged in different energy levels around the nucleus. Around the nucleus. The first three energy levels have a maximum capacity for electrons of 2 for the first one, 8 for the second one, and also 8 for the third one. Now, the current model of the atom is similar to this, but it's much more complicated, and that's what we're studying right now in Chemistry 30 in grade 12. I'm teaching the grade 12s about quantum mechanics and orbitals and Schrodinger's equations and things like that. So in grade 12, we'll study more of the current model of the atom. Okay, everybody needs to pay attention up here, guys. I know what you're laughing about. You're turning around. You should not be turning around. You Should be paying attention up here, okay? In grade 12, we'll learn more about the current model of the atom, which is a little bit different than this one. But this one is so close to what we think reality is like. This is the one we're going to study most, because you can learn a lot from this model, even though science has now changed the model just a little bit to make it a little bit more detailed. But we're gonna basically study this model for a little while. So, picture timeline. You guys need to draw this. Need to write this down. This is a little summary of what we've learned so far. So Dalton had the billiard ball pool ball model, solid, little tiny ball that was not divisible at all. It's uniform throughout. It's all the same throughout. The billiard ball. Thompson, plum pudding model, where we did have a ball, but there's little pieces of negative charges in there. So we went from Dalton to Thompson. Then Rutherford came along and said all that positive mush is not evenly spread throughout the atom. It must be centered in the middle there. So this is the positive part. Actually, I'll use red. So this is the positive region of the atom called the nucleus. And the electrons kind of like are somewhere around there. We don't really know where they are or what they behave like. And then Bohr came along and said, hey, we've got the nucleus, and electrons orbit the nucleus, and they have predictable paths, and he did a whole bunch of math and figured out sort of where these electrons might be and stuff like that. So this is the Bohr model. So these are the four main models of the atom. And like I say, we're going to kind of stop here. This is pretty close to what our current understanding is. Pretty close. And we're going to study this one about this because we need to learn about the atom, and this can tell us everything that we need to know really at this level in grade 9. So finish that picture timeline, put that in your notes so you have an understanding of what that is. Okay, so just one more note here. In chapter 5, Pearson, Saskatchewan Science 9, these are the questions that you'd be able to do so far for chapter 5. So we'll leave you that with your homework.